Um, I think quickly, because there are two new folks, maybe we'll just do introductions, and maybe I'll start just because I'm unmuted. So I'm Danny. I am a faculty member at Michigan State and the University of Oslo. I do computational physics education research, so I actually don't just sort of implement and teach computation, but my research is in how do students understand physics from computing, and how do they understand computing from physics. So I just from my picture, we'll go down to Andrew, maybe. So I follow a path here.
Sorry, yeah, I'm Andrew Morrison, and I teach physics at a two-year college near Chicago. It's Joliet Junior College, the country's oldest two-year college. And I have been interested in computation for a long time, ever since I heard it was Larry Martin, was that it, from North Park University? He gave a talk a long time ago when VPython was just sort of getting started. And this year, I finally implemented some coding projects in first-year physics for engineering physics, which I had hesitated to do for a long time because I felt like my curriculum's super full to begin with, and I kind of felt like not a lot of people were doing computation in the first semester. But I did a little taste of it last semester, and I did more of it for the second semester, which I'm teaching for the first time in like 6 years for various reasons. And, you know, I had some successes with it and some other challenges, but I'm really interested in doing more.
Cool. Marie, in my window, you're next.
Okay. Hello, my name is Marie Lopez del Puerto. I teach at the University of St. Thomas in St. Paul, Minnesota. And we got snow this morning, or last night, I guess. But it's all gone now. We're back to 50. I've been teaching the modern physics course this semester, and I've been using MATLAB and trying to do computational homework and computational labs. So some experiments and some computation, a mix depending on what the lab is, and computational exams. So today my students had a computational exam, and I've been doing this for 9 years now. This is my 10th time through this course, and it's always fun.
Cool. Ernie, we're just doing quick introductions for a couple of new folks, so if you don't mind.
Okay. Hi, I'm Ernie Behringer from Eastern Michigan University, and sort of recently joined into the whole Python game, and also was involved in writing the computational physics recommendation for the APT.
Cool. Josh, you're next on my.
Hi, everyone. I'm Josh Samani. I'm a lecturer at UCLA in the Department of Physics and Astronomy. And for the past year or so, my main computational implementation has been in these honors seminars that I created for upper division mathematical methods and for the lower division intro mechanics course at UCLA. This quarter I'm teaching a computational physics class for seniors, and just generally speaking excited about trying to integrate computation to all levels of the curriculum and hearing what people's ideas are. And I'm actually particularly interested, Andrew, in the sort of elements of you said there were certain successes and certain challenges and things, implementing in the intro course more deeply the computation. So I'm kind of interested in doing more in intro courses, and I'm a little bit concerned about the same thing, you know, the curriculum being pretty tight and all that. So I'm interested to hear more about that.
Cool. Kelly, you're next in my rotation.
Hi, Kelly Roos, Bradley University. I'm starting, well, next fall I will be starting my 25th year of integrating computation into my physics courses. So I've done about, you name it, I've tried it. Everything from Fortran and C to Mathematica and Python. So I guess you could say I'm an old campaigner in this. By the way, Andrew, you missed the workshop this last weekend at the ISA PT. Yeah, shame on you. All right,
I know. We can talk about Delta and Atlanta for the whole time if you really want.
Yeah, okay. Anyway, you're probably going to make it to the one in Rockford coming up, I presume, right?
Yeah, definitely.
Yeah. Well, we should do a workshop together, but we'll have plenty of time to work on this, all right?
I want to talk to you about that.
Yeah, certainly. All right, I shall stop talking now.
Okay, Michelle.
Hi, I'm Michelle Kucher. I'm a professor at Davidson College in North Carolina. I'm a computational physicist. I do computational physics research, algorithm development, that sort of thing. It's my first year as a professor, so I'm currently teaching computational physics, so a lot of computation in that class. Last semester, I implemented computation into the intro level labs. This year I'm not teaching, or this semester I'm not teaching an intro level lab, just the lecture, and I haven't implemented it there. So that's all.
Okay, last person I have is James, but I suspect that is not your first name, is it?
Can you hear me? Hello? Okay. I'm Floyd James. I'm from North Carolina A&T. So I may have to go visit Davidson up the road to see what you're up to. I started in computation, I guess about 10 years ago. I went to the Schroeder workshops. I went to the Modern Interactions VPython stuff. I created a computational intro course for our curriculum, and I started to work on a computational concentration. And then I stopped. So now it's time to start again. So now I'm starting to plan the computational physics concentration for our school. And I guess I got on this list because I went to the PICUP workshop in Atlanta.
Cool. Thanks. All right. So I guess the idea here then is to just sort of do a little bit of a share out. So I guess if they're not particularly sure where we want to start, but if people have sort of things that they've been doing that they want to share out, we could start there and see how the discussion evolves.
So I'll start because I realized I didn't actually say I'm doing anything like this semester. So there was like this long pause and I'm like, what am I supposed to say? Anyway, so this semester I'm teaching an advanced optics lab course. And what I'm finding is students need more practice in learning how to fit functions that are not lines. Okay, so anything that's not, just exactly a straight line or a polynomial is something they need practice at. And so they need sort of the computational scaffolding to do that kind of laboratory work. So that's one of the things that's been going on. I'm also teaching an algebra-based intro course in E&M, and I've done a little bit of glow scripting, just not asking the students to do computation, but rather just to use them as simulations, which isn't ultimately where I want to be, but it's where I'm at.
Ernie, how are you giving the students in your advanced optics course, what kinds of things are you having them do? I mean, you said you noticed that they're struggling with these nonlinear fits and so forth. What are you having them work on?
So one of the more recent things is we have them construct a laser where they have to align the last mirror to make it laze, and then I have them measure a beam profile. So it's an error function fit, that beam profile done with a knife edge. And And basically, I have to give them most of the code. Like Eric Ayers has a pickup exercise set on curve fitting, and so we can start from there. And even with that amount of help, they still need a little bit of hand-holding for that. So that's one example. The other thing we do is a light scattering experiment where the functional form is a sine squared. And so this is like two instances where you have nonlinear fits that they have to do. So to me, it's sort of more evidence that you really have to provide the proper scaffolding and a lot of support.
Have they ever seen like Law of Malice before getting to your class?
Not necessarily, but yeah, that's actually that's another of the fits that they have to do, is we do a simple Malice's law experiment, yes. And the interesting thing, right, is in the textbooks, there's no offsets or anything, right? And so they have to sort of recalibrate that, oh, it's not an ideal system, this is real. And there are offsets, there's background, etc.
I wonder if, like, I mean, I almost never get to polarization in intro physics, but you know, if there was a really simple like intro level version of that where you could take data and put it into something like Logger Pro and have Logger Pro do the fit, and then use that as the scaffold to get to them doing the fit themselves. I don't know if that would be faster or just take up too much time.
That's a good question. I think if you have something like Logger Pro, the temptation is just to use Logger Pro,
Right.
and not to develop, say, a code that's more flexible. So, but one can argue about, you know, where do you want to spend your time and their effort?
Cool. Thanks, Ray. Other things people are working on, other interesting projects, things that you've noticed this semester you can share?
I have something that I do want to share. I'll try to share my screen. I don't know how this works, but whatever. So one of the things that I kind of decided to do, I punched the share screen button. I don't know if it's my computer's thinking. One of the things I decided to emphasize was only doing computation for like stuff that we can't do in class. And so this is my trinket stuff. And one of the things that I was working on myself was if I have a ring of charge and then another charge comes in and interacts with that, what does it look like? And so I think this is it. So what I wanted to do was, release a charge near a fixed, near the fixed ring, and then watch it accelerate towards the ring, and then oscillate back and forth if it's right on the center line. And that'd be kind of cool. And that's something like we don't do the oscillation, math in the class. We could. It's actually not that hard. But I wanted to get to the point where we would release the charge not on the center line, and then the oscillation wouldn't be so simple. This is my code, and I'm not entirely sure if you can see the animation, but it worked really, really well, other than I never got I'm not great at optimizing this. And so it's kind of, there's actually quite a lot of calculation going on. And so it runs kind of slow and clunky or whatever. But on a personal level, I thought that was really cool that was something that, you know, I could come up with and then show the class and whatever, and then try to have them be inspired to do something similar, or actually just really more simple, and then like work up to that if they really wanted to. And you know, that was one of the things that that really encapsulates the having minor successes, but there were a lot of challenges along the way, because there was just a ton of I had several students who were very resistant to this, and I was very surprised by that. So,
Andrew, what preparation do they have when they get to this exercise, let's call it?
So for this one, we had done, I'd started with the electric field of a single charge, and like a single point charge, and they had to modify that. And then, actually I should go back to this. I don't know if you can see like all the shares and remixes and whatever. These are, you know, students had access to this and they were modifying it and so on and so forth. So after we did the electric field of a single point charge, then it was the electric field of 2 point charges. And this one. So this was the starter code, and they had to make changes to it to, like, there was a goal for this one. Yeah. So there were, they started with the same code as the single point charge, but then they had to add a second point charge at a particular location, so on and so forth. The other preparation that they had was that, so I had 24 students in the class, and all but 3 of them, I think it was, had me last semester. And we had done some rudimentary coding with, you know, forces and whatever. But I don't think many of them remembered. They remembered that we had done it, but I don't think they remembered any of the syntax or details or whatever. So, yeah.
Do you do this in your labs then, or?
Well, we use a studio physics approach, so the lab is integrated seamlessly.
Okay.
So
how many hours a week do you meet? Just curious.
We meet 6 hours a week. It's 7 contact hour, 5 credits, so it's 6 clock hours, if you will.
Gotcha. So you have the flexibility to do whatever you want when during any period, right?
Right.
Yeah. Oh, cool. And would you say that your style is to provide them with some kind of working code and have them modify it versus have them start from scratch?
Well, actually, so I I should preface this with I belong to a local community makerspace that I've been a part of for 6 or 7 years, and I've been playing with Arduinos, for example, for, I don't know, a few months after Arduinos came out. And I came to, and I run like local workshops at libraries and at the makerspace for how to program Arduinos and do stuff with that. And about 2 or 3 years ago, I came to this realization that, you know, I'd spent all this time with Arduino, and, you know, it was after working with it for 4 or 5 or 6 years that was like, there was one day that I had this idea for this project for an Arduino project. And I sat down and I opened up this blank screen and I just started pounding away and you know, coding up the thing that I wanted. And I stopped and I realized like it was like the first time that I had ever started with a totally scratch thing that, you know, wasn't just a modification of a modification of a modification, you know. And so I realized that, you know, it took me several years to get to the point where I could myself like write code from scratch, and that I got to that point by doing a lot of reading of code. Like, reading code is as important as being able to write it. And so to start from scratch with just like writing your own, you're actually like, you're always going to be copying somebody's code anyway. So I really believe that we have to teach students how to read code, and we have to honor the idea that a lot of people are just, when you're writing your code, you're modifying your own code or somebody else's code or something. And so why not like start with that from the beginning? So what I tend to do is I oftentimes don't give them fully working code, but it's sort of like a framework or a very minimally working code. And then we go from there, we build on it. So that's sort of how I approach it.
Gotcha. Interesting. Well, by the way, everybody, I don't mean to dominate the interview here. So jump in and ask questions if you have. This is really looks pretty cool to me.
I can stop sharing. I don't know if I don't really have anything else to add to my little show and tell.
Yeah.
I will say, I guess, that I was inspired to do that ring of charge thing because I had made a code where I did the problem where you drop a ball through a shaft in the earth and you watch that oscillate. And I mean, the electric ring, I mean, it's the same physics, the same math.
Sure.
And I had a lot of fun with that one because like you can put a skin on a ball that looks like the earth. And so I have an earth that is like partially transparent. You can see the ball. And then you can make the earth rotate. And so, there's a lot of fun things that you can do with it that are, there's actual physics to all the stuff I'm doing, but it's not necessarily, it's separate from the computational physics that we're trying to also really emphasize.
Right. Yeah. You mentioned that you said there were maybe 3 students that didn't, or a handful of students that didn't get into this. What do you think that was all about?
Well, so I'm at a 2-year college. We have a diverse, set of students. And I had one student who it was very much a personality thing that he's just struggling with. He's an interesting case because he wants to be a paleontologist, and I'm not entirely sure why he's taking engineering physics, but he came into my office and he told me that he sees no reason why he'll ever have to know how to write code because it has nothing to do with measuring the length of a tibia or something and whatever. So that was a struggle. But then I have another student who is, she's a 38-year-old single mom and trying to go back to school, become an engineer. And she's a hard-working student. She works full-time and studies really hard, but she's really traded at her computer. She'll spend 2 hours banging her head on a Microsoft Word problem. And so I don't know. It's those 2 were the 2 of the 3 that I didn't have last semester, and they basically decided, well, I've never coded before, and so I can't learn to code. And I'm like, that's like opposite of everything I set up my class to be about, just in terms of like, it's not even about coding. It's like, you're learning something new. That's why you're here. Like, I'm here to help you learn that thing that's new. And so like, let's figure it out together.
Right.
So I don't know if this helps at all, but I have coded a program that actually was measuring like the length of bones.
I would love to see that. That was
yeah. Go tell that one student.
I actually don't know what part of the body they came from. Like, people brought us these bones that they couldn't touch, and then we had to 3D scan them and take measurements, and then learn about the archaeology or whatever they were, paleontology. They learned something about it, but.
Oh, that's really cool.
Perfect.
Yeah, that's really interesting. I had this was about a year ago, so it wasn't this year, but a year ago I had a couple of I had someone from the county like medical examiner's office in my office like handing me MRI scans of a skull that they had imaged, and they wanted me to stitch it all together and come up with a 3D printed skull. And that was super fascinating. It had nothing to do with like physics. And
Sure.
like, you know, someone told them that I'm a 3D printing guy, and then I got a phone call out of the blue, and then they show up and detectives show up, and it was really interesting. So I should have actually told the student about that. But yeah, that's a great story. Thank you for telling me about that.
So I got a question. You mentioned that you did the ball dropping through the center of the earth, which meant you had to give a spherical mass distribution. How did you do that?
So I used a very simple model where you assume that it's a terrible model where you assume that the Earth is uniform density, and you get a pretty good estimate. And there's an interesting, I think it's AJP paper that compared the 3 different models of how you can get the density of the Earth. There's like a realistic model, and then there's like the fake model that I was using, and then there's something like in between or whatever. And it's really fascinating that between those 3, like the difference in the time that it takes the ball to go through the Earth is like it's like, I don't know, it's a small fraction. It's like 10% or 20%. It's really surprisingly you can get very close with a very bad model. So I was not using a good model.
So you did if you're this point in the Earth, then the gravitational force is this, as opposed to simulating the whole planet.
Right. Yeah. It's like,
okay. All right. Got it.
Right. It's like the mass version of Gauss's law sort of thing.
Okay. Got it.
Yeah.
Cool. Any other stuff people are doing or interested in?
I was going to share something I'm interested in and recently got interested in, but I haven't done anything about it myself. So I just keep hearing about machine learning everywhere, and it's just so hot right now. And my students want to learn about it. Everyone wants to learn about it. People want to get jobs in it. You know, it's just the hottest thing in the world, apparently. So I started learning about machine learning, and I started contacting faculty in my department who use machine learning to see if it's possible to integrate this into undergraduate curriculum, because it seems like such a blossoming field, and I'm sure a lot of undergrads are going to be using it if they go into careers in data science. So, you know, if anyone has been using machine learning or knows, has any ideas about implementing it in undergrad curriculum, I'd love to hear about that.
So I do machine learning in my research. We have in our computer science department, we have both a machine learning course and an artificial intelligence course, which like right now with where I'm at, like I tell students who are interested in doing research with me to take those classes. But I'm also interested, and I haven't done anything with this, I teach, a sophomore level computational physics class, and I've been told that perhaps I could teach an upper level class as well. And that one I plan to do some machine learning in. That being said, I haven't done that. So maybe that doesn't help you at all, but at least I'm also listening.
I got a dumb question for you. Are you talking something like a neural network sort of machine learning thing? Okay. What type of approach do you, or maybe what type of approach do you use, Michelle, in your research topics? I mean, I'm just curious. But
I'm probably most known for using Bayesian neural networks.
Oh, all right.
Just because like that's what my PhD was on.
Okay.
And in
Believe it or not, I know what that is.
Yeah.
Yeah.
And actually, it's really great. So teaching computational physics this semester with Mark Newman's book, we talk about a lot of the pieces that
Mhm.
go into making the Bayesian neural network algorithm without the learning aspects. So just like the basic idea of what supervised machine learning is, which it's a supervised machine learning method, and how we can use methods essentially that we already know, put together methods we already know to create a method that will learn.
Hmm.
So it's possible for
Okay.
people who have at least gone through Newman's book to
Yeah.
pick up that algorithm.
So I'm wondering, the context in physics or astronomy that I know about, that I've heard about recently, is sifting through astronomical data, and in particular things like identifying galaxies or galaxy clusters or whatever. I don't really know any astronomy, but tasks like that. But I haven't really heard about machine learning in the context of physics very much. So I'm wondering if you have any insights on like what sorts of applications people use it for physics.
So I see it a lot in the big experiments. So like I initially did it with work with the LHC and the CMS group at the LHC. They do a lot of machine learning to pick out signals, sort background from signals, actually a lot of different areas. And then we started to use it now as we're developing bigger detectors in nuclear physics at Michigan State. So I know like those are my areas that I know, and I see a lot of people. So even like getting into research areas I don't know a lot about, but like the long baseline experiments, I think that they also use machine learning methods. So I think it's everywhere in physics research, and it's used pretty easily in cases where you're essentially doing image analysis, because that's where a lot of like packages have already been developed in non-physics areas that you can use. And so I see like convolutional neural networks and like the deep learning type things where people can use or build off of what other people have done if you kind of have these images, which you do get a lot in physics experiments.
Do you think it would be hard to get access to like sort of somewhat small manageable data sets that we could give to a student and give them a little project, like a little machine learning project to work on in, say, like a couple of weeks?
No, I think that that's totally doable. Like often when I'm trying a new method, you do the simplest of things, like something that, so normally you'd use it on something that's high dimensional, so it's hard to fit or something like that, but you can do it on something that you know the answer to. So that's obviously, and it's simple to plot or something like that. So with like supervised machine learning methods, I have this one where I take like a plot, like I have a list of X values and Y values, and then I have this target that's sine of X times cosine Y, and that's a test data set where I know what, like if I'm plotting things, I know what it should look like and things like that, like just super simple things to learn. And also like finding things in images, like, but really basic images, like can you find a circle in this image of a circle? Now what if there's two circles or something like that, which isn't the physics per se, but then you could then do something physicsy after that.
Cool. Other thoughts, ideas? I have something that I can show y'all. I don't know how useful it will be. So one of the things that I've been working on my upper level course is how to sort of integrate more computing actually into the actual instruction. So so right now I'm teaching advanced E&M 2 for majors, and I'll be teaching it again next year. So this past year I taught it a little bit with a little bit of computing, but I didn't actually do any computational instruction in the class because I found it really, well, awkward. The lecture courses or the lecture rooms that we teach in make it really awkward to sort of do all of those things at the same time. But But then I went to Norway and I learned about a piece of software called DocOnce, which is, if I can share my screen. Hold on, I think it must be this guy. What are you seeing? Am I sharing my screen? Did you see a cat? Sorry.
Yes.
The
Okay.
Norwegian cat.
Yeah, sorry. Okay, that's the right thing that I was meant to show you because I think that was the right. Okay, so this is a set of slides that we are working on for our faculty to integrate computation. So I'll show you what it can do, and then I'll show you what the thing actually is. So basically, it makes slides in Reveal, which is a web-based sort of presentation software. It's relatively simple, so forth. Yada yada yada, a bunch of crap because the person who developed this likes to write lots of things. So it handles markup that is latex markup, so you can actually have equations and so forth. So here, basically this is just talking about to our faculty, we can solve lots of different 2-point boundary value problems. We can do them in a lot of different ways. We should think about maybe how we do that in our courses and so forth. There's some discussion of the Toeplitz matrix and how you can turn this problem into an eigenvalue problem, and how it can be used for lots of different kinds of problems, including the solving for the energies in the hydrogen atom, or hydrogen-like atoms, if you will. But eventually, it gets to this idea. Sorry, he has a lot of stuff here. So this is Python code that's actually inside of the Reveal, I guess, presentation. That code can be evaluated live. It's apparently powered through SageMath, and so you can get a plot. So this is one of the eigenvalues, and this is a plot of this radial probability as a function of R, sitting inside of this presentation. So never left the presentation. The code is in there, and so forth. Now the other thing I'll show you is what does that look like when you write it, and it has a really funky syntax, but it's kind of like a markdown syntax that is not terribly hard to learn if you are used to hold on here, sorry, it's this guy. If you're used to doing some sort of markdown. So in this particular, can you all see you probably can't really read it in detail, but there's some title, there's some author, some date, slide titles, there's figures and so forth. The interesting thing is, sorry, I'm just going to scroll all the way down. So
looks like the Atom editor, right?
It is the Atom editor, yeah. So here's just actual math. So this is just LaTeX that gets processed by it. So you could type your regular LaTeX into it. The other thing, let me get all the way down there eventually. Once you've installed DocOnce, here it is. So here's that Python code that I showed you. So it's set off by this sort of begin code command here. And then this is actual code in Python. And that's what you would have seen in detail. And it can be evaluated. Essentially, that begin code, end code tag gives you code in there that you can go through and run and evaluate, and it runs through Sage Math Cloud and shows you the figure. The other thing that it does, this is one last, so the thing about DocOnce is the name is not just a slightly clever name, I guess. I don't know, maybe it's not really that clever. It's odd. Sorry, I gotta do it by terminal because I have some problem here with where I'm located. Nope, that's not what I want. Basically, it can create lots of different kinds of things. So lots of different kinds of file formats, sorry. So if you, for example, at the same time, so all that is just markup, right? And it processed it into a reveal situation. But it can also, where did that open? Sorry. Somehow I ended up with a full screen Zoom app, and I don't know how I did that because I didn't request it. But you get things that you don't request there's a joke there about Donald Trump, but we'll leave it at that. Here we go. So this is a PDF that was generated from the exact same markup. So this is some write-up that could be handed to students in some way, and it has the same LaTeX in there, and I think eventually when you get to the code, it'll have the code written up. It can also do handouts of the same kind of thing. It can render it into IPython notebooks. So like all of that text will be text, and then there'll be IPython notebooks that you can edit. So it has lots of different kinds of features to it in the sense that you write it once in this doc1 syntax, and then you can it can be processed into a variety of different kinds of things, so that you can use it in class as a presentation. You could use the exact same syntax to generate a homework or an exam problem or what have you. You can use the same thing to generate a LaTeX document that the students could work from, and so forth. It's surprisingly flexible, to be honest. So this is something that I'm going to probably start moving my markdown slides to next semester, so that I can start including code.
Can you spell that out? What you're saying, Danny?
Yeah.
Doc once?
Yeah, DOCONCE.
All right.
Doc once. Yeah, I can send you.
And is there a package that you just install this into your Atom editor, or?
Not that trivial, as it turns out. I can share stuff with you that makes it more trivial. So essentially, it's there it is. There, it's a
okay.
there's a GitHub repository that has it. Essentially, you just build it. So you clone the repository, then you use Python to just set it up. It needs a couple of libraries, which it doesn't actually tell you that it needs, which is fun to find out later. So if you need help setting it up, let me know. Once it's set up and sort of linked to your Python installation, it's pretty straightforward to do all of the things. The syntax is a little bit of a learning curve, but if you've used like Markdown, or if you've used LaTeX or something, it's kind of similar. It has just its own sort of curiosities about it.
Mm-hmm.
What was the other thing I was going to mention about it? Oh, so it has its own sort of commands. So it becomes basically an application that you, or like a command that you can call in the command line. The thing to do is actually build a make file that does all the things you want it to do, and I have some of those that I'd be willing to share that just essentially just generate all the things. You just call it once, and it generates everything you need without having to remember its particular syntax.
So this is the coolest thing I've seen this week. Can you clarify a couple of things? First of all, so you said reveal and doc once. What's reveal? And also when you were saying that it's the code executed from the browser using Sage Math Cloud, which meant that it wasn't running locally, but it kind of looked like it was running locally. Can you just clarify those things for me?
Yeah. So basically doc once is a markup language, and so it's a markup language. Like LaTeX or HTML or Markdown or whatever, but it can generate LaTeX, it can generate Sphinx, it can generate HTML, IPython notebooks, Markdown, MediaWiki, and then those things can be post-processed. So like it can generate LaTeX, and then in your makefile you can have it call all the things to make PDFs in different ways. The reveal is essentially the HTML that it can generate. So you can tell it to generate HTML in the style of reveal, which is essentially a JavaScript, a set of JavaScript codes that allow you to make entirely web-based presentations. So they don't require like PowerPoint or Keynote or what have you. They're written in plain. They're written in HTML, but what a lot of things do is actually take Markdown and pipe it to the form of HTML that uses that reveal JavaScript.
So can I ask for, then I'm a little confused then, because I'm familiar with Reveal, and when you were showing it, what I assumed was that you had written all the Reveal stuff and then put in some extra stuff, the doc once thing, inside the Reveal. Is that what you did, or did you?
Nope.
You did the doc once,
Yep.
and then that generated Reveal?
Yeah, so I can show you the quick thing I could show you if I can get to it quickly is here. Let's do it really fast here. So this is let's see if it'll open. So here's the makefile that is written for this. So when I want to create a Reveal document, there's a series of tags or a series of options that you put in that Doc once understands, and it grabs those things from its own package and sort of just, it uses its markup to know when to basically make like slide breaks and so forth. So there's special little commands like that it interprets when you compile it in a certain way, but it dispenses with when you compile it in another way. For example, there's a split command that you put in that would that gets read in by the compile when you make it a Reveal presentation, but it gets thrown away when it's a LaTeX document, right? So it just generates the whole LaTeX document without that stuff. But if you say I want a Reveal document, it parses that as something that's important. So and then there's a bunch of stuff here, but all of those are shareable and just sort of like kind of learn by editing or making changes to it and so forth. Sorry, so there was Michelle, I think you had another question. I don't remember what it was.
Oh, I think what you didn't answer is where the Python or whatever you had, the code was running.
Yeah, that's a good question. I have not yet unpacked where that is happening exactly. It says powered by Sage Math Cloud. I haven't tried to use it on a machine that doesn't have certain packages or something to see if it fails, or tried it without an internet connection to see if it fails, because it's not clear to me. I haven't actually I guess the easiest thing to do would be to view the source on that particular slide and see what it's doing. I haven't done that yet.
Okay.
So that's my share.
And you're going to share that with us, right?
Yes. Well, share. I can share the
Files.
anything that you want. You're welcome to.
I'll take it all.
Sure, fair enough. So I should say that the documentation is a little hard to parse. It took me probably a week or so to really sort of learn, for it to become more intuitive and to know what I'm looking for, because they also refer to things. The documentation refers to things in strange ways because it's written in English, but it's written in English by people whose second or maybe third language is English. So the words that you might use for certain things are kind of hard to remember sometimes, or they're not exactly the words that we might use. Okay, well, it's about 5 minutes till 10. So folks have any other things they would like to chat about? Or are we feeling pretty good? Josh left us. Oh, he must have hated Doc once. Cool. Okay. So I guess I'll go ahead and stop the recording.